Hello, welcome back to another video. We're going to be talking about proofs involving quantifiers, the second part though. So in the first part, we talked about how to deal with quantifiers when they appear on the right side of the table. So maybe I should draw the table first. This is the to prove side of things, and this is the what we know side of things. And so we've dealt with quantifiers and how to deal with them when they appear on the right side. Now we're going to see how we deal with them when they appear on the left side. So let's start with the for all quantifier on the left side. What are the ways in which we can use this as a resource in order to draw some connections or prove things? Well, here's one thing you can do. Try to read this statement out, see what it actually says. It means that for all x values, p of x is satisfied. Essentially, this means that you can replace x with any value you want and have that resulting statement still be correct. For example, I can replace x with the number 17 and have p of 17 be correct. And since, well, p of 17 is correct, it's something we know to be true, then we can put it on the left side of the table, the what we know table. And somewhere along the lines, maybe this will be helpful in order to prove something. Now obviously you can't just replace it with any value you want. This has to depend on the universe of discourse. So if you forgot what that means, so the universe of discourse is basically what is the allowed value for x. So is x here supposed to mean for all numbers, for all vectors, for all shapes, for all complex numbers maybe? It depends. And how would we identify the universe of discourse? Actually, our brain handles this part pretty well on its own. Like I said earlier, our brain, especially when it comes to logic, it does things automatically and subconsciously. For example, and it does this based on context. So for example, if this proposition, it means x has an area greater than 0, then you automatically know that the universe of discourse for x should be shapes, right? You can't put a number here, a number can't have an area, so you're supposed to put shapes. Like for example, this triangle here has an area greater than 0, sure it has. This weird thing here, that's also a shape, it also has area greater than 0. So your brain automatically knows that we're dealing with shapes and not numbers or vectors or any other mathematical object. So you shouldn't really worry about the universe of discourse. It's usually very obvious. So yeah, if we're talking about shapes, then we can replace x with any shape and make it be true. So for example, p of a square is true, but p of 3 is not true because the number 3 can't have an area basically. So it's difficult to screw up, okay? And you will definitely know what are the allowed values that you can substitute in for x and have everything still work out and be okay. It just makes sense. If we're talking about shapes, then you can substitute in any shape. If we're talking about numbers, then you can substitute in any numbers, and so on and so forth. So that's how we deal with using the for all quantifier as a resource in order to prove something. So let's actually use it and see it in action. Let's prove something. I want to prove that A is a subset of A. And again, our brain really likes to be on autopilot mode. It's forgetting a quantifier here. So we should actually put the for all quantifier there. Because when we're saying that A is a subset of A, we are not making any assumptions about A. A is arbitrary. We're not restricting A. Because when we're making this statement here, A is a subset of A, we actually mean any set. Like any set is a subset of the same set itself. For example, the set 1, 2 is a subset of the set 1, 2. And the contents inside of the set won't matter at all. You can change it to be whatever you want and the statement should still be true. That is why the for all quantifier is appropriate here. And again, this quantifier over here is not necessary to be placed because it's a piece of information that should already be intuitive. Like I said, the for all quantifier is very easy to forget because our brain automatically adds it in for us. But I think that writing the full and complete details for each step is important. So I will write every single detail and I will not leave any gaps behind. So let's keep going. I want to prove this, and let's use something that we learned from the previous video. We learned that if A intersect B is equal to A, then A is a subset of B. This is something we proved in the last video. So since we know this to be true, we actually prove this theorem, if you want to call it that, then we can put it on the left side because it's something that we know already. And again, we're forgetting the quantifiers. The sets A and B here, they're not talking about the specific set. In fact, they're talking about any arbitrary set. So we can just say for all A and for all B. There we go. Alright, what's the next step? Well, we said if we have the for all quantifier, then we can substitute in certain values. And well, we're talking about sets here. That is our universe of discourse, so we can replace A or B with any set we want. Now it's very tempting, considering that we're trying to prove A is a subset of A, to substitute B for A. So let's do that. If we substitute B for something else, then we can simply ignore the quantifier. So let's do that. Substituting B for A, I mean. So A intersect A is equal to A implies A is a subset of A. Alright. Oh, actually, yeah, I forgot to write the A here. So for all A. Now, these things are a bit annoying, so let's get rid of them. What did we say we have to do when the for all quantifier appears on the right side? Well, we can just let A be arbitrary, and we can simply get rid of the quantifiers. So let A be arbitrary, and I'm not going to write that down here, but just it's something that you should keep in your mind. So from now on, when we're talking about A, we're dealing with an arbitrary set instead of, well, a specific set, for example. As long as we keep that in mind, we should be fine. Okay, so imagine if we had this piece of information, right? Imagine if this is on our what we know list. Then we would be done, because what do we know? We know that if this is true, then this should also be true. And we know that this is true, therefore, if we combine these two pieces of the puzzles together, then we would get A is a subset of A as another new piece of information. And then we could draw the connection between these two, and we'd be done. So, to actually complete this proof, we need to prove that A intersect A is equal to A. So let's add that there. A intersect A is equal to A. So once we prove this, we can basically add it here and we'd be done. Proving that two sets are equal, we've done this before. Basically, we have to prove that if X is in A intersect A, then X is in A, and the other way around. So if X is in A, then X is in A intersect A. But if X is in A intersect A, what does that mean? X being in A intersect A. Well, if X is in the intersection of two sets, then X is in both of them at the same time. So this means X is in A and X is in A. So look at this. Basically, you're just repeating the same thing again. You're saying X is in A and X is in A. You're repeating the same thing. So it would make sense for this to be equivalent to X being in A, because you're just repeating the same thing. This entire section over here should be useless. But that's what we obtained using intuition, so let's try to actually prove it. We'll prove that if we say any statement and if we repeat that, then this will be equal to P itself. So we can do that with a truth table. So we have P here, and P can be either true or false. That's our only two possibilities. And we have P and P. So it's pretty difficult to see how we're supposed to fill this in now. But if I were to draw another P, and well, since this is P and this is P, it should be the same, then we can easily fill this in now. For an AND statement to be true, both these guys need to be true. And well, that's what we see here in the first universe. So let's put a true here, and since both of these are false, we only actually need one of them to be false, but if both of them are false, then this should also be false. And now you can see that P and P is equivalent to P. So we have proven this statement here. Now since we know that they are equivalent, this should be simple. We can replace this guy over here with x is in A because we've shown that it's equivalent. And similarly, we can replace this with x is in A because they're equivalent. And now this is basically prove this guy and prove this guy, but they're both exactly the same thing. So our work is simplified to proving one statement only. How do we prove this statement over here? What did we say when we want to prove P arrow Q? Well, it means that we can move this to the left side. So let's do that. And we'll see that our work is immediately done. We put x in A over here. And we're done because look at the connection between the two. So there we go. That's our proof that A intersect A is equal to A. So since we have proved this guy at the top over here, we can simply put it onto the left side. A intersect A is equal to A. And well, like we said before, we can combine these two pieces of information to conclude that A is a subset of A. Therefore, we are done with the proof that A is a subset of A. And notice across our entire proof, we didn't use this forbidden step, let A be something, something, something. Because if we add this step in, then this proof would only work when A is one specific set. And well, that's contrary to what the question asks for. The question asks for all sets A is a subset of A. And this just breaks that rule completely. But since we didn't do this at all in our proof, we should be fine. This proof works for any set A, whatever it is. Alright, so that's how we use the for all quantifier. Now let's take a look at the existence quantifier. So now what if we have the existence quantifier on the left side of the table? How are we supposed to use this as a resource? Now it's basically just the same thing. The only difference is you can't replace x with anything. This just tells you that there exists an x, which makes the statement true, right? So basically there exists an x, but you know nothing else other than the fact that it exists. So you can call this x, this mysterious x, whatever, you can call it xo. Usually that's the notation that they use. The O is actually a 0, I think, so it's not XO, it's X0. So you can say, for example, PX0 works, and you can use this somehow in the construction of your proof. Now you don't know what X0 is. Maybe you can find it out later, maybe you don't need to find out what X0 is, but basically, yeah, this is the information that you get from the existence quantifier. That there exists an x, we'll call it x0, and that p of x0 is true and it works, and we might be able to use it somehow. Alright, so let's see how we're gonna do that. Alright, so let's see an example in action. Alright, so what are we gonna prove? It's actually a pretty long statement, so I'll put the bullet point over here. What we want to prove is that if this is true, okay, if this is true, so this is one whole statement over here, that this whole statement over here implies this statement, right? So it looks awfully complicated, but just think of these two things as separate statements. So this whole thing implies this whole thing. Alright, so it looks very scary at first, but just do things methodically, yeah. Okay, so we have a statement of the form if P then Q, right? So what do? We just carry this whole thing over to the other side. Right, so everything looks, well, much simpler now. And what do we do now? Well, there exists an X that makes this entire statement over here true. So let's write that down. Px0 implies Qx0. So if this is true, then this is true. So that's what we know, that there exists an x0 that makes it so that this statement works. Okay, well, we have another arrow statement over here, so we can move this to the left. Let's just do that. Oh yeah, this should be exist x. Yeah, so hopefully that didn't confuse anyone. This one should be like that. Alright, cool. So what now? Well, we have a for all quantifier here, and we dealt with that just a few minutes ago. What did we say we can do when we encounter a for all quantifier? It means we can substitute x for anything that we want. Now the problem is, what do we substitute it with? Notice that we have this thing over here, which means if we have this guy over here, if we're able to put this down onto the left side of the table, then we would be able to get qx0, which is getting closer to our answer. So now that I've told you that, it seems pretty tempting to replace x with x0. So let's do that. We know that this works for all values of x, so it's definitely going to work for x0, right? So we just replace x with x0 and everything should be fine. x0, there we go. And now that we have this, now we can simply combine these two and we're going to get qx0. Alright, but we're not exactly done yet. These two still don't quite match, but we're almost there. How do we prove something when there's an existence quantifier? We must set x to be equal to something, right? So set x to be equal to something, and we have to show that the proposition holds true. Right, so now that we have set x on the left side, we can erase the existence quantifier because we only need to show that it works for one particular value. So what particular value makes this thing true? What can we set x equal to make this statement true? Well, how about x0? If x is equal to x0, then, well, the thing above over here turns into q of x. Right? Because just x is equal to x0, so we can just replace x0 with x and everything will be fine. And now we're done. We have this guy, and they both match. So we are done here. And for the most part, this amount of logic is all you need in order to prove a few basic theorems. But some of them will require more advanced techniques such as induction. So we'll cover that in the next video, and I think I'll have one final video after this, which is about how to actually write a proof, because like textbooks, they don't explain the proof like this. This is just a systematic way of solving it. The thing is, after you do all of this work here, you would have to communicate that information, and you don't communicate that in terms of a table. You do that with words and writing. So we'll see how to properly translate this table work over here into proper writing. So see you in the next video.